Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will talk about the probability distribution of one of our parameters in a simple linear regression model. Our parameter of interest in this video is the slope, beta1. Okay, before we talk about the distribution of beta1, let me remind you that in order to perform hypothesis tests and set up various types of intervals when using the simple regression model, we need to make certain assumptions about the error term values, the epsilons. These error term values, the epsilons, are assumed to have a normal distribution with mean 0 and variance sigma square. And any one value of the error term epsilon is statistically independent of any other value of epsilon. Okay? So, given the model, let me remind you what our model looks like. Yi equals mean level beta 0 plus beta 1 times xi, so that would be the particular value of the predictor for the ith observation, plus a random fluctuation epsilon. There we are. Okay. So, and as we said, what we are assuming is that epsilon I has a normal distribution with mean 0 and variance sigma square. Okay. And that's an assumption, okay? So, and that the epsilons are independent. Okay. And also, as we mentioned in another video, sigma square is the same regardless of the value of the predictor variable xi. So these assumptions imply that yi is normally distributed with mean beta 0 plus beta 1 xi and variance sigma square. Okay, so let me write that down. Our assumptions about epsilon I imply that yi is normally distributed with mean beta 0 plus beta 1 xi and variance sigma square. as we are about to see, these assumptions about the epsilons also have distributional consequences for beta 1. We will show that given our model and distributional assumptions for epsilon I, hat beta 1, the least squares estimator of beta 1 is normally distributed with mean beta 1 and variance sigma square divided by sxx, or sigma square divided by the sum of xi minus x bar, the whole thing square. Okay, so let me just write that down. We will show that given our model and distributional assumptions for epsilon I, hat beta 1, let me find it somewhere. We should have a hat here. There we are. Oh, sorry, not what I want. Let me first have a beta 1 and then a hat. Okay, now the hat beta 1, right, is going to be normally distributed with mean beta 1, this guy, and variance sigma square divided by sxx. Okay? Okay, so that's what we're going to be showing in this video. And that's what we're doing. Now, why are we doing it? Well, in the near future, this result will be very useful to derive hypothesis tests and confidence intervals for this estimator, beta 1. Make sense? Okay. So if you will, we could write it down here just to be super specific. What are we doing? Doing this. Why are we doing it? This result, will be useful to derive hypothesis tests and confidence intervals for our estimator beta 1. Okay? Okay, great. Let's show this result. Okay? Our starting point will be the expression we already have for hat beta 1. Okay? We have already derived the least squares estimator of beta 1. Let me write it down. Least squares estimator of beta 1 remember that we used the normal equations to come up with a general expression of this guy. It was kind of a homework problem. We did it in a particular case, and then in our slides we have a general expression, and what we said is going to be a homework problem. For instance, you could derive it using the inverse approach, right? The inverse matrix approach, or Kramer's rule, right? Okay, so anyway, let me write it down for you. We already have that expression for hat beta 1 or beta 1 hat. Okay, so it's a ratio between two quantities. One way of writing it down would be something like this, and you will find that notation in our textbook, in one of our textbooks, at least, but maybe in both of them. Chances are in both of them. Sxy divided by sxx, and what we mean is just in the case of the numerator, it's the sum of cross products of xi minus x bar times yi minus y bar, right? And in the case of the denominator, it's just the sum of the xi's minus x bar squared. Okay, so let me write it down here. Xi minus x, but we want x bar here. Yeah. Oh nope, not the one I want. That's the one I want. Great. And then we want yi minus y bar. And then we have something similar. We don't have y's here. This case, we have a square. Make sense? So this kind of notation allows you to easily remember these expressions, right? This is the sum of the cross products, centered cross products, if you will, and sxx is the sum of the squared deviations with respect to the mean. Okay, or x. Okay, so the key, right, the key here will be expressing this estimator, this beta 1 hat, as a linear combination of yi's. Why is that going to be so important? Because we know that the yi's have a normal distribution, and from statistics 256, from statistics 260, we know that a linear combo of normals is normal, and that would be something that we could easily show using MGFs, for instance. Okay, so let me just write that down. if we could show that our estimator beta1 hat equals C1 times y I plus C2 y2 and so on, Cn yn, where n represents the total number of observations that we have, and the ci's are constants, where the ci's are constants, we are basically done. Okay, so that's our goal. And again, if we can express our estimator beta1 hat as a linear combination of normal random variables, well, we know from statistics 256, statistics 260 that the linear combination of normals is normal, right? And we can easily show that using the MGF approach. Okay, so an intermediate result will be that this guy here, this numerator in the expression that defines beta1 hat, the sum of xi minus x bar times yi minus y bar turns out to be, right, the same as an expression that only has to do with yi's. It turns out that this xi minus x bar times yi minus y bar is the same as the sum of xi minus x bar times just yi. Okay, so that's an intermediate step. So let's do that intermediate step because it's going to be really helpful. An intermediate result will be that, as I said, we'll see, let me try and copy this, that cross product happens to be, let me copy that again here, the sum of xi minus x bar times yi minus y bar is going to be the same as just, oh no, just let me remove this. Okay. Okay. So let's show that. Okay, let's show this equality. We're going to start from the left hand side, and then we're going to end up with what we have here on the right hand side. Okay, so proof. we're going to expand what we have here. So this, the sum of xi minus x bar times yi minus y bar, happens to be the same as this. Just going to expand here, right? Let me remove that bracket here. Oh, no, come on. There. And let me be lazy here. Oh, okay. Maybe not. And then xi minus x bar. Okay, you guys agree that's the same? Just you know, expanding. Okay, so note that the first term is what we want, right? So if we could show that this second term here equals 0, we are done. Okay? If we can show that this guy, the second term, is 0, we are done. We are done. Okay. So let me start here from the left hand side. Note that y bar is a common factor, so I'm going to pull it out, right? I'm going to factor that out. So this, the sum of xi minus x bar times y bar, happens to be the same as y bar times the sum of xi minus x bar. You guys agree? Okay. So I have y bar here. Now let me just do the sum. In this case would be the sum of xi's. Minus, and we have the sum of x bar. I goes from 1 to n. So this, right? I'm just doing the following sum. X bar when I equals 1, x bar. When I equals 2, x bar. I equals 3, x bar. Up to n. So this is the same as n times x bar. But if you recall that x bar is the sum of xi divided by n, n times x bar happens to be just the sum of xi's, right? So let me just do one more step here. I'm going to say x bar is just sum of xi divided by n. You agree? That's the definition of x bar. These cancel out. You have the sum of xi minus xi, well, the sum of xi's, right? So this is going to be the same, so this is going to be 0. Got it? So let's summarize. We wanted to show that the sum of xi minus x bar times yi minus y bar equals the sum of xi minus x bar times yi. So we just started from the left hand side, we expand it. This is almost what we want. We go and say, hey, if we could get rid of this guy, we're done. And we have shown that this second term is 0. So it's gone, we're done. Okay? Okay. Great. So we have that intermediate result. Okay? Let's remember why it is that we wanted to do this using this result. We can express beta 1 hat as follows. Now instead of doing this, instead of using beta 1 hat is the sum of xi minus x bar times yi minus y bar divided by xi minus x bar squared, right? The sum of those guys. We have this. And can you see that that is taking us one step closer to the ultimate goal? What was the ultimate goal? The ultimate goal was expressing this guy as a linear combination of yi's. So if we define this, the sum of xi minus x bar divided by the sum of xi minus x bar squared as our well, if, let me rewind here, if we define ci as xi minus x bar divided by the sum of xi minus x bar squared, right? If we define that as our coefficient, then we have beta 1 hat is the sum of some ci's times yi. Let me write it down. Here we go. We claim that we're expressing, thanks to this, beta 1 hat as a linear combination of, as a linear combination of yi's. Okay, let me just be super specific about what the ci's are equal to, where ci as I said is going to be xi minus x bar, right? xi minus x bar divided by this sxx or the sum of the xi's minus x bar squared. Okay? You could write it down like that too. Let me write it down like that as well. It's going to be useful. SXX. Okay, make sense? Okay. So we are almost there, right? Hey, guess what? We were able to express our estimator beta1 hat as a linear combination of yi's. And since the yi's are normally distributed, then that implies that beta1 hat must have a normal distribution as well, right? But we know that normal distributions are fully specified when you have their mean and their standard deviation, right? Okay, so before we find the mean and the variance of beta1 hat, we're going to talk about three important properties of these CIs, these coefficients we just defined. Those properties, those three properties that we're going to be showing, will be very useful to easily find the mean of beta1 hat and the variance of beta1 hat. Okay? Okay. So a little bit of a detour, but it's going to be a good idea in the end. It's going to save us time, and it's going to make the derivations so much easier to understand. Okay? So first property of our CIs, property 1. It turns out that the sum of the CIs equals 0. Okay? Sum of CIs equals 0. Oops. Got it? Okay. Let me show that. Okay? Proof. Let's start from the left hand side. Oh, come on. Okay, we're going to start from the left hand side. Let me remind you that CI is just the sum of xi minus x bar divided by sxx, right? So let me write it down here. Now note that sxx is the sum of xi's minus x bar squared. Once you find it, it's a number, right? So this guy is going to be a common factor. It doesn't depend on the index I. As I said, once you find this number, the sum of squared deviations with respect to the mean of x the predictor variable is a number, and it's the same number for all these guys, so you can just factor it out, and that's exactly what we're going to be doing here. Then we have the sum of the xi's minus, its mean. But guess what? We are going to have sum of xi's minus n times, what's the definition of x bar? Xi, well, the sum of xi's divided by n, right? So we're going to end up with 0. We have seen that here, right? Can you see it? Right? Let me write it down again. So this is the same as the sum of xi's minus n times x bar, right? But n times x bar is the same as the sum of the xi's, right? Zero. So we're done. Make sense? Okay, remember, x bar, sum of xi's divided by n. So the n's cancel out. You only have the sum of xi's, and then these two guys are the same. Difference 0 times this 0. Okay, so that's property number 1 of our CI's, our coefficients. Property number 2. Property number 2. So the next property is the following. It turns out that the sum of CI xi equals 1. Okay. Let me try and be lazy here. CI xi equals 1. Okay? Okay. Let's show that. Proof. Well, you guys agree that 1 equals s xx divided by s xx. Now it turns out, right, that sxx is the same as the sum of the xi's minus x bar squared, right? Let me write it down here. xi minus x bar squared. Let me use sxx there. Okay. Now, the numerator happens to be the same as this. xi minus x bar squared is the same as xi minus x bar times xi minus x bar. You guys agree? Now, you guys remember that to show that beta1 hat is a linear combination of the yi's, we had something similar here. We had yi minus y bar, and we ended up with the sum of xi's minus x bar times yi back then, right? So doing something similar to what we just did to show the to derive the equivalent expression for beta1 hat, right? You will have this. Okay, again, it's going to be the same trick. If you have like 3 minutes later today, just do it. Just expand and you'll see that the same trick works. Right? Okay. All you have to do is expanding, right? And realizing that the x bar here, right, can be factored out, and then show that that second term is 0, and that's it, right? The same trick that we used for the cross product. Okay. So okay, remember how we defined the CIs? Well, it was xi minus x bar divided by sxx. So this happens to be just the summation, the sum of CIs times xi. Okay, so that's it. CI xi. We have shown that the sum of CI xi equals 1. That's the second property that we wanted to show. Okay, and we're done. Okay, good. Last property. This one has to do with the sum of the CI's square. Okay, here we go. Property number 3. Sum of CI's square, that will be equal to 1 over s xx. Okay, here we go, s xx. Okay, there we are. Proof. Just copy this. Proof. Well, we're going to start in a very similar fashion to what we have been doing. We start from the left hand side and just start expanding and so on. Okay. So remember that CIs are just you know, xi minus x bar divided by sxx, right? So let me write that down. Xi minus x bar sxx, but that's a CI and we want to have CIs squared. Okay, so great. Note that what we're going to have is xi minus x bar squared divided by sxx squared, but sxx squared will be a common factor, so we're going to be pulling that common factor out. 1 over sxx squared, right? Times summation of xi minus x bar squared. Got it? Okay. But see this expression here? You go, hey, hold on, wait a minute. The sum of xi's minus x bar squared, that happens to be sxx, right? So this is the same as sxx divided by sxx squared, and well, that happens to be just 1 over sxx, and we are done. Make sense? Can you see it? Right? We just used the definition of the CIs, xi minus x bar divided by sxx. We square it, right? This guy is going to be a common factor. We pull it out. We realized that this
the sum of xi's minus x bar squared is, by very definition, sxx, and that's it. So that's the third property. The sum of the ci's squared equals 1 over sxx. Make sense? Okay. So, we're almost there. Now, we're going to be able to easily show what the expected value of beta 1 is. Okay? Here we go. Let's open a new one. Okay? So, let's find expected value of beta 1 hat. Beta 1 hat. Our estimator, right? That was the ultimate goal, finding the expected value of beta 1 and the variance, right? Because we have already seen that beta 1 hat is a linear combination of yi's. So we already know that our estimator will have a normal distribution, but now we are going to find its parameters. Okay, so expected value of this guy. Well, we have already shown that we can write this down as a linear combination of yi's. You guys agree? Now, we want the expected value of beta 1 hat. Right? Okay. So, now you want the expected value of a sum. The expected value of a sum equals the sum of expected values. Right? So let's use that property. Our mathematician friends would go, oh yeah, the expected value is linear, so we're using the linearity of the expected value. Make sense? Okay, now we have the expected value of a constant times a random variable yi, so we get to pull out that constant, right? So that's the same as sum of ci times expected value of yi. But using our model, remember our model looks like this: yi equals beta 0 plus beta 1 xi plus epsilon I. Well, the expected value of yi happens to be, when you take the expected value here, this is a constant, beta 0 plus beta 1 xi, expected value of a constant, and the expected value of epsilon I is 0. So the expected value of yi is just beta 0 plus beta 1 times xi. You guys agree? Okay, let's keep going. So this is going to be just ci times beta 0
plus beta 1 xi. Okay. Are we good? Okay. So now let's expand this. This is going to be the sum of ci times beta 0. Ci beta 0 plus sum of ci times beta 1 times xi, right? So summation of ci beta 1 xi. Now beta 0, that's a common factor. Let's pull it out. This is going to be the same as just beta 0 ci plus beta 1 is also a common factor. Beta 1 sum of ci xi and here's where what we did before pays off, right? Remember that we showed 3 properties? Well, these properties will be very, very useful. So remember that the sum of the xi's was 0, right? So, oh, sorry. So this, the sum of the ci's is 0 by property 1, right? And the sum of the ci's times xi equals 1, right? That's by property number 2. So what we have here is beta 0 times 0, and that's by property 1. By property 2, what we have is beta 1 times 1. Okay? So let me just say that. By properties 1 and 2. So in the end, we only have beta 1. So bottom line, the expected value of beta 1 hat equals beta 1. So the expected value of our estimator is the true parameter. That has a fancy name, remember? From statistics 260, when that happened, what we said was beta 1 hat is an unbiased estimator of beta 1. Make sense? Okay. Good, good, good. Now, let's find the variance of our estimator beta 1 hat. Okay. Let me try and be lazy here a little bit. Let's find the variance of our estimator. So the variance of beta1 hat is going to be the variance of a linear combination of yi's. We know that the yi's are independent. So if we have the variance of a sum of independent random variables, the variance of a sum is the sum of variances, but only when those random variables are independent. So that's worth noting, right? Let me write it down here, because yi's are independent. Okay. So since we have a sum of independent random variables, the variance of a sum is the sum of variances. Now, we have the variance of a constant times a random variable. We get to pull out this guy, but not exactly as is. We have to square it first, right? So what we're going to have here is ci squared times variance of yi. Okay? Okay. Now, again, let's go back to our model to find out what the variance of the yi's is. Okay? According to our model, our assumptions about the epsilons are going to lead us to this. The variance of the yi's is sigma squared. Okay? Okay. So we have that the sum of ci's square times the variance of yi equals the sum of ci's squared times sigma squared. Let me write it down here. But that sigma square is a common factor, so we get to pull it out. So what we have here is that the sum of ci's squared times sigma square is the same as this, right? Let's just pull this guy out. But you guys remember that the last property of the coefficients of the ci's that we showed had to do exactly with this, the sum of the ci's squared. And what we did is we showed that that happens to be 1 over sxx, right? By property 3. So let me just say this, that what we're going to be doing next is by property 3. Sigma square times 1 over x, x. And that's what we wanted to show, right? That's going to be the variance of beta1 hat. Okay, so wow, it was kind of long. Well, let's recap before we finish this video. Recap. What we did here is we showed that beta1 hat has a normal distribution, and we found its mean and its variance, right? And the mean of beta1 hat happens to be beta1, meaning our estimator beta1 hat is unbiased, and the variance of our estimator beta1 hat happens to be sigma squared divided by sxx. Okay, so in summary, we have shown that beta1 hat is normally distributed with mean beta1 and variance sigma square over sxx. Make sense? Okay. Well, thank you so much for watching. Take care and keep working hard. See you next time. Bye.